Data types, discrete and continuous. Welcome to this session. Let's begin with a fundamental but critical concept, data types. Why do data types matter? Because they define everything we do in data analysis. First, they determine how we measure a variable. For example, is it categorical, like color, or numerical, like temperature? Second, data types influence which statistical tools or charts we can use. Using a bar chart for continuous data or a mean for categorical data would lead to inaccurate analysis. Third, they help us collect and analyze data properly. Understanding the type of data helps ensure we use the right format, units, and techniques. The bottom line here is simple yet powerful. Choosing the wrong data type leads to the wrong analysis and ultimately misleading results. This is why getting the data type right is one of the first and most important steps in any analysis. Let's look at the two main types of data we work with in Lean Six Sigma: discrete and continuous. Discrete data refers to counts or categories, things you can count or classify. These values are non-continuous, meaning they take on fixed values. Examples include number of defects, pass, chew, fail outcomes, survey ratings. Continuous data, on the other hand, involves measurements. These can take on any value within a range, making them infinite in nature. Examples include time length, weight, temperature. Why this matters? The type of data you're working with determines what tools, charts, and statistical tests are appropriate. For example, you can't use a control chart meant for continuous data on discrete data, and vice versa. Always identify your data type early in any analysis process. Let's now dive deeper into discrete data. Discrete data refers to values that are countable and finite. You can't have partial values here. This type of data is typically used when you're counting occurrences, classifying items into categories, or making yes/no type decisions. We'll explore 6 types of discrete data. The first one is A. Count data. This is exactly what it sounds like, counting how many times something happens. Examples include number of defects per batch, number of errors per invoice, number of patients visiting a hospital each day. So whenever you're answering the question, how many? Zrenia, we likely working with count data. Let's continue exploring the types of discrete data. Next up is Anchquise, Claudine. B. Percentage data. This type of data represents the percentage of a group that shows a specific result. It still qualifies as discrete because it's derived from count-based outcomes within a group, though it's expressed as a percentage. For example, a 5% defect rate in a production run, 80% of customers reporting satisfaction, 12% absenteeism in a department. These percentages come from dividing one count by another, like 5 defective units out of 100 produced. Use case? Typically, we use a P-chart or attribute control chart to monitor percentage data over time. Now let's look at the third type of discrete data. C. Binary data. This type is the simplest form of discrete data. It has only 2 possible outcomes. Think of it as yes or no, pass or fail, or 1 and 0. These binary outcomes are extremely common in decision-making and classification problems. Examples include a product being either defective or non-defective, a customer either registering a complaint or not, a loan application being approved or rejected. Use cases. This data is perfect for P-charts, which track proportions of binary outcomes over time. It is also widely used in logistic regression, especially in predictive analytics, where we model probabilities of Let's move to the fourth type of discrete data. D. Nominal data. Nominal data is categorical and has no inherent order or ranking among the categories. You can think of it as labels or names that are used to identify different categories, but without any numerical meaning or sequence. Examples include defect types such as scratch, crack, or dent. These are just names, and none is greater than the other. Departments like sales, IT, or HR. Again, categories with no order. Machine IDs, say A, B, and C. Just identifiers, not ranks. Use cases. This type of data is great for Pareto charts, where we see the frequency of categories to identify the vital few. Also used in chi-square tests to analyze whether observed frequencies differ from expected frequencies. Now, let's look at the final category of discrete data. E. Ordinal data. Ordinal data is also categorical, but unlike nominal data, it has a clear inherent order. However, the difference between the categories is not measurable or consistent. Think of it as ranking or rating. Examples include customer rating like poor, fair, good, excellent, clearly ranked, but we don't know how much better excellent is compared to good. Education levels such as high school, college, graduate. Again, ranked in order of progression. Employee performance. Below expectations, meets expectations, exceeds expectations. Use cases. Often analyzed using median analysis, since the mean isn't appropriate. Also used in ordinal regression, which respects the ranking but doesn't assume equal spacing. So, in summary, nominal binds categories with no order. Ordinal binds categories with order, but no measurable gap between them. Next up is a broader category, attribute data. F. Attribute data. Attribute data is a general term used for qualitative data, data that answers a yes/no question or classifies items based on attributes. It's not measured on a continuous scale, but rather evaluated based on conformance to a criterion. Examples include pass-fail outcomes during an inspection, parts being conforming or non-conforming to specification, audit results, where compliance is recorded as compliant or non-compliant. In all these cases, we are classifying the data into groups based on predefined rules. Use cases. Commonly used in attribute control charts, like P-chart or NP chart. Also used in attribute gauge R and R studies, where we evaluate consistency in subjective assessments. Important note, attribute data can be binary, yes, ja, no, nominal categories with no order, or ordinal categories with order. But what makes it attribute data is its qualitative nature. Let's now summarize when to use discrete data and understand some of the challenges that come with it. When to use discrete data. Use discrete data when you're dealing with counts, categories, or classifications. For example, how many defects? Which department? What type of issue? It's commonly collected during inspections. Defect logs, pass/fail records, checklists. These are typically yes, no, true, false, or select from a list types of data. Challenges with discrete data. While discrete data is easy to collect and categorize, it has some limitations. Less precise than continuous data. You don't get a detailed measurement. Requires larger sample sizes to reach statistical significance. Fewer statistical tools are available. Most are non-parametric, which have lower power. You often need to convert categories to numbers carefully, especially with ordinal data. Example challenge. Say you collect survey responses on a scale like poor, fair, good, excellent. That's ordinal data. You cannot calculate a mean for these categories. Instead, you use median or mode to summarize. Let's now shift our focus to continuous data, which is different from discrete data in that it can take any value within a range. What is continuous data? Continuous data is used for measurable quantities, Think of data that can be fractional or decimal. It is not limited to set categories or counts. It has much finer precision. Examples of continuous data. Time, e.g., 4.53 minutes to complete a process. Length, e.g., a material is 12.245 centimeters wide. Temperature, e.g., oven temperature reads 165.2 degrees Celsius. Weight, e.g., a package weighs 3.25 kilograms. These examples show that continuous data is captured on a scale and allows more granularity than discrete data. When to use continuous data? Whenever you're measuring something. Quantities, how much. Dimensions, how wide, long, heavy. Performance metrics, like cycle time, response time. Typically, continuous data is collected using continuous data, definition and usage. Now let's talk about continuous data. Continuous data can take any value within a range, like time, temperature, weight, or length. It's measured, not counted, which makes it very detailed and powerful for analysis. However, using continuous data does come with some challenges. First, we need calibrated measurement systems. If our tools are off, our data will be too, leading to inaccurate conclusions. It's also more prone to measurement errors and rounding issues. Since we're working with precise numbers, even small mistakes can skew results. Before using parametric statistical tools, we must check for normality. Many of these methods assume that the data follows a normal distribution. And finally, we need to perform a measurement system analysis, or MSA. This ensures that the way we're collecting data is reliable and consistent. So while continuous data gives us richer insights, it also demands more care in measurement and analysis. In this slide, we are comparing two fundamental types of data: discrete and continuous. Let's start with measurement. Discrete data represents counts or categories. Think of things you can count individually, like the number of defects or pass-fail results. Continuous data, on the other hand, involves measured quantities. These are values that can fall anywhere within a range, such as time, weight, or length. Next, in terms of values possible. Discrete data is finite. It includes integers or labeled categories. You can't have half a defect or 2.3 passes. Continuous data allows for infinite possibilities within a range, including decimals and fractions. Now let's look at examples. For discrete data, typical examples include the number of defects found on a product, or whether a part passes or fails inspection. Continuous data examples would be how long it takes to complete a process, the weight of a package, or the length of a component. Finally, when we talk about charts used, discrete data is typically represented using P-charts, U-charts, and Pareto charts. Continuous data uses tools like the X-bar R chart and histogram, which are ideal for analyzing variability and distribution in measurements. Understanding the difference between these two types of data is essential because it directly affects the tools and statistical methods we use in quality control and process improvement. Discrete versus continuous. Comparison. On this slide, we're comparing discrete and continuous data, two fundamental types of data we use in process improvement. A key advisory here is to select the correct data type, because it directly determines the appropriate statistical tools you can use. Using the wrong method for the wrong data type can lead to misleading results. Also, be cautious with ordinal data, like customer satisfaction ratings: good, fair, poor. These look like they have an order, but they're not interval or ratio data. Don't average them. That's a common mistake. Whenever possible, we prefer continuous data. Why? Because it gives us more flexibility and options for analysis, such as control charts, regression, and hypothesis testing that assume normal distribution. Lastly, if you're working with discrete data, especially coded values, make sure the coding is clearly defined and consistent. For example, ensure that everyone understands that 1 equals yes and 0 equals no, and that this is applied uniformly. In summary, know your data type, treat it correctly, and when in doubt, lean toward continuous. Practical examples in Lean Six Sigma. Let's bring it all together with some practical examples from real-world Lean Six Sigma applications. Starting with manufacturing. A continuous data example would be measuring the diameter of a shaft. This type of measurement allows us to detect small variations that could affect product quality. A discrete data example is counting the number of defects per shift. This is a count. You either have a defect or you don't. In service industries, we might track customer wait time, a continuous variable, to improve responsiveness. On the discrete side, we could measure the percentage of calls resolved at first contact. This is a binary outcome, resolved or not. And finally, in healthcare. For continuous data, think of patient blood pressure readings. These are measured on a scale and provide detailed information. For discrete data, consider infection versus no infection. It's a yes, no outcome, a perfect example of discrete, categorical data. So, as you can see, both types of data are used in every sector, but selecting the right one helps ensure accurate analysis and effective improvements. Key takeaways. Before we wrap up, let's review some key takeaways from today's discussion on data types. First and foremost, always clarify the data type before beginning any analysis. Misclassifying data can lead to using the wrong tools and drawing the wrong conclusions. The data type directly influences what statistical tools, charts, and hypothesis tests you can use. For example, continuous data allows for more powerful tests, while discrete data often requires non-parametric methods. It's also important to understand the strengths, limitations, and challenges of each type. Continuous data offers precision, but requires reliable measurement systems. Discrete data is easier to collect, but often less detailed. And finally, remember that both discrete and continuous data are essential in Lean Six Sigma projects. You'll encounter both, and using them correctly is key to effective problem-solving and decision-making. So always start by identifying the data type. It sets the foundation for everything else in your analysis.